and binary search trees are actually fairly straightforward. They're fairly easy to code. And one of the questions I love asking, which I ask a version of this on the practice exam, and I'm going to do it right now, and it's pretty much the exact same. It is the exact same question I ask on the exam, just with different numbers, which is, given this list of numbers, insert it into a binary search tree. Draw the resulting binary search tree, right? So, like, say the first number. So, a binary search tree, the big thing about it is that it keeps everything in order. How are things kept in order in a binary search tree? Anybody? Yes?
You put smaller numbers on the left and then bigger numbers on the right.
Right. That's exactly right. You're given a root. We're given some root value, right? We've given some root node. Everything less than the root goes to the left side. Everything bigger than the root goes to the right side, and that is recursive. That's a recursive property, right? It's true for your for the root's left subtree and the root's right subtree. So it just keeps going on and on and on. So let's go ahead and let me go ahead and draw a very small binary search tree. I'll start with 5 over here. We've got 3. And then I've got let's say 12 over here, right? So the smaller values smaller than the root have gone to the left. Bigger values have gone to the right. So how does it add? So can anybody tell me how adding an item to this tree works? How would it work if I wanted to add 1 to this tree, right? How would that work out? Yes.
Will you go to the left of 5 because 1's less than 5?
Right. Go to the left because 1 is less than 5.
And then you compare it to 3 and 1's less than 3, so you go to the left of 3.
Yep. So basically, you just simply travel down the tree until you find an empty spot. It's a really easy algorithm. You find an empty spot, and you just find that, and you know what that empty spot is, just simply based on, is the value I'm comparing to smaller or bigger, right? So, what about how would inserting 4 go? How would that work out? Yes.
Go down from 5 as smaller, so you go left.
Yep.
And then you're at 3, it's larger, you go right.
Yep. So you put 4 over here. Right? That makes sense to everybody? Inserting is fairly straightforward. What if I wanted to insert the value -2, let's say? -2. Yes?
Would be to the left of 1.
It would, yep, we'd end up at the left of 1. -2 is less than 5, less than 3, less than 1, so -2 would go over here. And finally, what about inserting 7? Inserting the value 7, any takers? Yes?
Bigger than 5, go to the right.
Yep.
If it's less than 12, go to the left.
Yep. And there's pretty much no change for the way this works for addition. There's no weird cases we have to handle. Now with remove, with delete, there are some weird cases. But fortunately, here this is all adding some stuff to a tree. This is how it works. Now we can add anything that's comparable. Yes.
How would you add like another 3?
How would I add to another 3? So that is actually an exercise left to the user. But yes, you watch the video, so
You go to the right of 1.
you can go to the right of 1. Yes. So it depends on it really depends on how you decide you want to handle it for your tree. So some textbooks say no duplicates allowed ever. If you see a duplicate, just stop, right? So that's one solution, right? Because that's kind of an edge case. And then you could decide, well, duplicates, they're smaller than the original or larger than the original, right? And I like to just go with the rule that if I have a duplicate, it's smaller than the original. I don't give duplicates on exams, right? But it's just simply, but it's a great edge case. It's a great question. What if you have a repeat? And the answer is you're generally not going to have a repeat. But if you do, you have to have a policy that's consistent, right? You don't want to say, well, right for some and left for some others, right? Because otherwise you'd get completely lost with there. Okay. So, okay. Now let's go ahead and just to emphasize this, the other way. So these are comparable. Anything that's comparable works. So so we can use this for strings, right? Say the root of the tree is hello. Okay. So what if I wanted to insert the word blizzard into this tree of strings? Where would blizzard go? It would go to the left. And why is that? Because I know greater than and less than don't really work for this context, but that's what the comparable says. If you get a negative value when you use your compare to method, it says if it comes before this, right, if it's less than, that translates to coming before the root, it goes to the left. If it comes after the root, it goes to the right. Right? So if I were to do, let's say boondoggle, okay, where would that go? That would go to the left, right, because it comes before hello, but boon comes after blah, so it goes to the right over here. I assume this is how you spell boondoggle. I have no idea. I've never actually spelled it or seen it spelled. So now insertion generally. So as I've mentioned, insertion in this is really into trees is really efficient. Insertion generally takes log n time, generally. But there are cases where it can take O of n time, when the tree becomes horribly, horribly unbalanced. An example of this is that if we basically say, okay, if you're inserting stuff into a tree in order, like here, let's insert 1. Now let's insert 2, so that goes to the right. Now let's insert 3, so that goes right, right. Now let's insert 4. Now let's insert 5. Right? Now let's insert 10. Now let's insert 6. Now let's insert 7. Right? So it's resembling less of a tree and more of a really badly drawn linked list, right? Where each insertion is equal to the number of items it takes. Now this is an issue that you can get with binary search trees, and the way that it gets solved is in chapter 9. And next week we'll go over the operation that solves this. We're not really going to get into it just simply because of time restraints, but going over how to do what's called a tree rotation, which is what we'll do as an in-class exercise next week, is really, really good practice for kind of just figuring out how to do stuff. But in this case, when a tree becomes unbalanced, it can take O of n time to insert stuff. The vast majority of trees, when you actually use a tree, they're self-balancing. And balancing a tree takes log n time. So it will add something, check to see if it needs to be rebalanced, and then it will rebalance it in log n. So in practice, all trees take log n time to do everything, which makes it a great generalized data structure for just keeping track of stuff. So we've talked about adding, right, which is one of the questions that's going to be on the quiz, right? And my question is going to be pretty straightforward. My question is, here's a picture of a tree. I'm going to add this thing to it. Which of these other pictures of the tree matches what happens? That's the question that's the question you'll get on that. So the flip side, of course, of add is removal, right? So let's go ahead and draw a binary search tree. Let's do 7, 9, 8, 12, 15, and 13. Then on this side, let's go with 5, 6. Let's actually go with 4, 5, 6, and 2, 3, 1. And there was a reason I kind of went that way. So deletion is easy or hard depending on the case. Okay? Depending on so the way you delete something is first to say I want to delete 6. All the deletion algorithms follow the first rudimentary steps, which is that, am I the thing that needs to be deleted? No? Okay, is it less than me? If so, go and find it in the left tree and then delete it. Or if it's not in my left, or if it's not an appropriate value, that would be in my left tree. If it's not less than me, then I'll check my right tree instead and try to delete it there, right? That's essentially the recursion there. It's actually the base case that when you find it, that's the difficult part, right? So let's say we want to delete 6. I'll look for 6. 6 is less than 7. It's greater than 4, greater than 5. 6 is equal to 6, so we found the value to be deleted, right? So there's 2 easy cases and 1 hard case, right? Can anybody recall what the easy case for deleting a node is? Yeah.
Leaf.
When it's a leaf, right? To delete a leaf, it's very simple. You just do this, right? Because you can just remove a leaf from the tree, and there's no danger of like destroying the structure of the tree, right? That's why why deleting a tree is deleting a leaf is pretty easy, right? A leaf being an external node, a leaf has no children, right? So if you delete a node that has no children, all you have to do is just simply remove it. The way you remove it is you just simply tell its parent, hey, set me to null, right? Right? Set your left child or your right child, whatever I am, to null, right? That's all you have to do, right? And presto, changeo, leaf is gone. So the other case is, what if you have one child? So let's go ahead and restore 6 to its proper place, right? And this time we'll delete 5 from the tree. So 5 is less than 7. It's greater than 4. We found 5. Now we need to delete 5. And all we have to do, and the way that works is you just simply have your parent adopt your child if you have one child, right? And so in that case, 4 adopts 6, right? That doesn't change the structure of the tree at all. The structure of the tree is maintained, right? We deleted 5. Nothing really has to get reoriented or anything. There's no real changes there, right? Now the problem arises. So if you're deleting a node with one parent, you just have the grandparent. So your parent adopts the child, right? The problem arises when we delete something that has 2 children, like this root over here, right? If we want to delete 7. Now it depends on whether you want to. And that's because you can't just replace it with any node here, right? You think, okay, we would just move up 4 or 9, but actually moving 4 up here, right? Then you'd have 5 and 6 are both greater than 4, so they'd have to get shuffled over to the other side, and that's a lot of work. So then what we try to do is we cheat, essentially. What we do is, we literally cheat. We try to reduce this to an easy case, okay? What we do is that and as I go over in the algorithm in the video, what we do is we find our next in order predecessor or successor. Now, I go into, which means basically I find the thing that's either the biggest, basically I find the value that's closest to the root. And that can be either the value that's closest bigger or smaller. And just simply for convention's sake, I'll always choose finding the smaller, basically the biggest thing that's smaller than me. That's what I'm looking for. I'm going to be we'll replace the root by the biggest thing that's smaller than me. Now, you might think that's a pretty tricky task to find it, to do that, to find the biggest thing that's smaller than me. And the answer is it's actually kind of easy to do. What you do is you go into your left subtree, right, because that's where all the things that are smaller than you are. And to find the thing that's the biggest thing that's smaller than you just step into your left subtree, right, and then you go all the way to the right. You go as far as you can to the right. And once you can't go to the right anymore, you found the biggest thing that's smaller than you, right? So step to the left, all the way to the right. This is the biggest thing in the subtree, right? And I can kind of prove it, right? If it wasn't the biggest, if it had a right child, that thing would be bigger, right? So that thing would be the biggest thing. And if it had a left child, and if this thing over here had a left child, well, that would be smaller, right? And then anywhere up the chain, if we had gone left, well, it would be smaller than this, right? So the biggest thing is all the way to the right. So essentially, you step 1 to the left, and in the code, you can see you step all the way to the right. And what we do is that we just simply take this value, copy it up here, okay? Some people say swap the values, whatever. You just copy that value up here, and now you delete this value. And now because you went all the way to the right, you're guaranteed to be in one of 2 cases, right? So we've changed from deleting the root to deleting this guy over here. And since we've gone all the way to the right, that's guaranteed to be one of 2 cases. It either has no children, in which case it's super easy to delete, remember? Or it has one child, in which case you tell your parent to adopt that child, right? Which is also an easy case. That makes sense? So the way you do, so now let's go ahead and say I want to delete 4 from this tree. 4 is less than 6, so we go to 4. Okay, now we found 4, we need to delete it. So how do we delete it? We find the thing that's biggest in the left subtree. So we go 1 to the left and all the way we can to the right. So we replace 4 by 3. And then we erase the original 3. So any questions on that at all? Right? Any questions on that? Yes?
So when you did the 7 one, at the top, the root?
Yes.
Yeah, so, just like, can you say one more time the steps you went?
You step into your left tree, so you step one to the left, and then you step as far to the right as you can. That's always the algorithm for if you have 2 children. And then once you can't go to the right anymore, you found the biggest thing in the subtree. So you take that thing and you move it up to the root, and so now it's been replaced by the root. Sorry, now you replace that root and you delete the thing you just copied over, right? So for instance, if I were to delete, so let's see, just trying to think another one over here. If I wanted to delete 9, right, I would step 1 to the left, and then go all the way I can to the right, which happens to be nowhere, right? So that's the node that it will be replaced by. So 8, so 9 gets replaced by 8, so we copy over 8 over here, and then we delete the 8, because it has no children.
So I wanted to get rid of 15 now.
Now if you wanted to get rid of 15 is fairly straightforward because it only has 1 child. So we just simply have 12 adopt 13. Right? 12 adopts 13, just like that. That does lead to an interesting question, though, like what should I do if this is my tree? Right, if I get, let's go ahead and redraw this before I add. Right, let's go with 1, 3, let's go with 1, 4, 2, 3, right? Suppose I want to delete, and here there's obviously just a bunch more stuff, and drawing a triangle like that just simply is a shorthand for saying, and there's the entire subtree over there, right? So say I want to delete, I want to delete 6 from this tree. I go 1 to the left, I go all the way to the right, which is the 4, so that's what gets copied over. So now we are reduced to the case of deleting 4 from this tree, okay? So it has only 1 child, so I have 4's parent adopt my child, which means that 1 adopts 2. So this becomes 2, 3, like that, right? Okay, everybody feel like they got it? Okay, so there should be a tree quiz. Okay, I spent way too much time on this quiz, but fortunately that was me from the past who spent way too much time on this quiz. So I just simply get to revel in the glory of very nicely drawn LaTeX figures. So the quiz passed.